Okay. So today we will continue with the van der Waals gas and phase transitions. I think at least the thermodynamic description of phase transition is going to be the last lecture. So what do we know and what do we remember? We do know that dP to dV is less than 0 for any kind of description. What we have seen that if we are using ideal gas formula, okay, where is PV equals nRT. R is the gas constant, T is the temperature, and the number of moles. That from this picture, P simply equals to nRT divided by V. So if we plot different isotherms, so each line, this is P, this is V, each line is a specific temperature, so I plot specific T, and an R are constants. What we are getting is just lines that diverge when V goes to 0, and they converging towards 0 when V goes to infinity. And nothing really bad happens to ideal gas. Now, why is that? What is the problem? What?
The red one is...
No. So all of this, this is the behavior of ideal gas. I'm just reminding you what we have done, or at least mentioned, at the end of the last lecture. There are no phase transitions, no abrupt jumps, and we do know that phase transition, when it occurs, something abrupt must happen. There should be some sort of a jump in the pressure, in the volume, in the entropy, and for the ideal gas, nothing happens. Okay? Absolutely nothing. Now, why is that? If you remember, ideal gas, so what's the whole point of ideal gas?
No interaction.
Absolutely no interactions. So if I have a chamber, okay, if I have a chamber, and inside this chamber are sitting molecules of the gas, okay, and they are traveling into different directions, right, with different velocities. The whole point of ideal gas is that there is no interaction between any molecule A with any molecule B. They never meet each other, they never perform some sort of a collision, nothing. Right? Those particles are not colliding with each other. They do collide with the walls, right? But they do not collide with each other. Now, in phase transition, think about it. For example, in phase transition, what is going to jump? What is going to jump is the volume per molecule, or the entropy per molecule. Those are the parameters that are performing abrupt changes. Now, if there is no interaction, right, I can change the temperature, I can make the whole chamber smaller or larger. As long as they do not interact, they don't really care about it, right? So everything goes smoothly from one place to another. This is why, for each temperature in ideal gas, the lines are perfectly smooth, and this condition is always satisfied. Okay? This basically means that interactions are crucial ingredient in order to get a phase transition. Right? I cannot get, so this is just a bunch of particles. I don't care if I have here an Avogadro number of particles, or I get one single particle, because they do not interact. And one single particle cannot perform any phase transition. It's not interacting with anything, and it simply stays one single particle. Nothing really changes. Right? This is the problem with the ideal gas. And that's what van der Waals understood by saying, well, I need to include in this description of ideal gas, this description over here, some sort of interaction. effectively. Okay? So what van der Waals have done, he included a specific interactions which are based on what? Based on that those particles are not a point masses, but they have some sort of a intrinsic volume. Okay? So this is assumption number one. They are not mass point masses, but they have intrinsic volume. And B, the pressure, that in ideal gas, the pressure comes from what? The pressure comes from collisions between the particles and the walls. Okay? The pressure has to be also changed a little bit due to those effective interactions between the particles. They might attract each other, or they might maybe push each other out of their way, but there should be some sort of interaction. Okay? And this is why van der Waals has written his equation as P plus A n squared divided by V squared, V minus N B equals to N R. Okay. So the right hand side stays exactly the same, and the effective interactions that should be present inside the gas are entering through the, well, the pressure is not the same. It's modified, might be a little bit smaller, actually the real pressure because of the intrinsic interactions. And the volume, it has to be a little bit larger. Why? Because there is an intrinsic volume for each molecule. It basically means that volume cannot get zero, right? We cannot compress the system too much and shrink all this chamber to zero volume, right? Because there is always some sort of an intrinsic volume based on the actual sizes of those molecules. Yes?
I can understand why you added n times b.
Yes.
But I can understand why you added n. Exactly, I've been
Okay, so this is ideal, right?
Yes.
So I cannot shrink it too much. P is basically saying the real pressure, which is this guy, and this guy, this is what we measure. Let's think about it in a high temperature. In high temperature, we assume that the particles actually do not interact. So this is the pressure that we measure, okay? Whatever stands here in the parentheses. But the actual pressure is a little bit smaller. Why? Because they attract each other. So he assumed that the molecules attract each other, so the real pressure is a little bit smaller than the actual pressure. Okay? This was his assumption. Okay, so let's start, and as we plot this guy over here, let's try and plot the behavior of P as a function of V in this guy. Okay, so if we solve this, right, so we have P plus A n squared divided by V squared equals to N RT divided by V minus MB, and P equals minus A n squared divided by V squared plus N RT V minus N. So instead of plotting P equals nRT divided by V, we're plotting this equation.
Number of moles or number of particles?
Number of moles. So you can treat it as a number of moles, then this constant is something, a number of moles, and this is a gas constant, and you can treat it as a number of particles. Okay, so we still need dP to dV smaller than 0, and instead of this equation, we're using this equation. Okay, so what we are going to get? Now, if the temperature is high enough, right, we're still getting this curve, which is gradually decreasing. It is going diverging as V goes to 0, and it's converging to 0 as V is going to infinity. Great. So this is T1. Now, if we decrease our temperature a little bit, let's go to T2, it is still looks like that. Okay, so those are isotherms. This is T2. Now, a surprising thing starts to develop when we decrease our temperature even further. It starts to look like this. Okay, so it's still monotonically decreasing. Okay, but we see some sort of a saddle point that starts to emerge at lower temperatures. So T1 is larger than T2, it's larger than T3. And when we decrease our temperature even lower,
It's an ideal gas.
this is not an ideal gas. We are plotting this. So let's erase this. This is van der Waals gas. VDW gas. Okay? So if we decrease our temperature even lower, we will start to see an appearance of a maxima and a minima for this function. This is T4. T3, T4, and we decrease it a little bit smaller than this will repeat itself.
It does not reach zero though, right?
Sorry?
It does not reach zero.
It does not reach zero. It does not reach zero. Okay, so what's the problem of having those guys over here? This is a problem. Why I'm telling you that this is a problem?
Because liquidity is
Okay, because this condition has to be satisfied always. Okay? So when I have a minima and a maxima, basically the derivative of p with respect to v is larger than 0 in these regions, here and here. Okay? Now, what do we say to that?
Not in equilibrium.
It's not an equilibrium. Okay. Or, but this is an equation that should describe equilibrium, right? Oh, so maybe something that related to phase transition, right? Something that related to phase transition. But the thing is, the moment that my theory predicts something which cannot be defined in equilibrium, this is an equilibrium condition. Each system, physical system, okay, 99% of the systems that are in equilibrium should satisfy this equation. The moment that this equation is not satisfied, I say what? I say, well, there is something wrong. Either it's out of equilibrium, or my equation is wrong. Something is really, really, really bad with my equation. Right? And the suspicion is, and this is what we know about gases, we know that gases, they can become liquids, and sometimes they can become solids. Right? So this behavior, which basically tells us that an equilibrium cannot be achieved in this area, points out that, well, this equation is wrong and something other happens. What this something else? We call it a phase transition. Remember, in the phase transition, we should obtain some sort of a jump. How do we see this jump over here?
So you're saying that when we're in phase transition, it's not an equilibrium, or this
No,
equation is wrong?
even in phase transition, we have to be in equilibrium. But this equation is simply wrong in this area because it describes a continuous transition, right? Everything here is continuous. It's a continuous function. What do we know? We know that a phase transition is discontinuous. So van der Waals theory,
An approximation.
it's A, an approximation, B, it fails to produce fails to produce the description of a phase transition. Okay? So when phase transition occurs, this condition is not satisfied. There is a problem with the model, and we have to fix it somehow. Because what do we expect to observe for a phase transition? P and V. Right? What do we expect? We expect that, well, there should be a decrease to some point, right? Call it V8. And then there should be a jump to a point VB. Okay? And then, again, gradual decay. So this is phase A. And this is phase B. Let's consider that this is a liquid and this is a gas. Exactly. What happens? There is a jump in what? There is a jump. So this area over here, in theory, in phase transition, the system, it does not live with VA plus VB divided by 2. There is no volume of the system that can be VA plus VB divided by 2. So all of this is a restricted area from thermodynamical point of view. The system is not living over there. So any theory that I would have cannot tell me that is something nice happens over here. You see what this theory predicts? This theory predicts that, well, it will go down, go up, and then go down again. This is nonsense because this guy is not satisfied, right? So intrinsically, when we're plotting those PV curves, they're in phase transitions. There should be restricted areas where this phase transition occurs. Okay? So any model that gives us this behavior, the only thing that we can take out of it, well, whenever you have this, that dP divided by dV is larger than 0, this is some sort of an area where we expect the system to perform a phase transition. That's all. The fact is that fundamental physical condition for equilibrium is not satisfied is simply telling us that there is a phase transition that occurs over here. Okay? So it tells us the system cannot be here. It can be to the left and it can be to the right. In the middle it can be. But this is exactly what we expect from a phase transition. We reach a specific point, P, right? And when we do something, something abrupt happens and we jump immediately to another volume. Right? We have seen that in phase transition the volume is actually jumping. This is what you see in liquid to gas transition. Right? Boil up a water and you will see it happening. Yes?
It jumps as it remains the pressure.
Okay, so at constant pressure, let's assume that I'm in this point and I will decrease my pressure a little bit by epsilon. It will immediately jump to 40. Right? So you have to modify something. Here is some sort of an equilibrium. What happens is that part of the system is in VA and part of the system is in VB. If you remember.
So it can be in VA plus VB, just not all the systems one.
But it's not a continuous mixture of anything. What happens is that I have part of my system which is gas and part of my system which is liquid. Remember? At this point, I have not a mixture. Part of the system is gas, part of the system is liquid. Right? Exactly at the critical point, exactly at the phase transition. Okay. What happens a little bit above? I'm here, all the system is liquid. I'm over here, all the system is gas. Exactly over here, it's not a continuous mixture. They are separated. There is a phase separation that occurs at this point, and the whole system is jumping. Okay, here everything a little bit to the right, to the left. Everything is liquid. A little bit to the left, everything is gas. Okay. Exactly the point. It's a mixture. Somehow, and it depends how you reach this point. It really depends on how you reach. Think about it. If you're reaching from this region, so you liquid, you're reaching to this point, everything is liquid. You decrease your pressure a little bit, and then all the system suddenly jumps to the mixed state, to the state of gas. It really depends on how you approach the phase transition. Yes.
מה זה הגרף השחור הזה שסיפטת בתוך החלק של בין הליקוויד?
So this is the behavior of the van der Waals prediction, and it's not true.
אוקיי. ואתה בעצם אומר שישר אנחנו צריכים לקפוץ משם.
Yes. Okay, so if this is not true, we can use all of this that my system is performing some sort of a non-physical behavior we can use this non-physical behavior in order to describe when the phase transition is going to occur for the van der Waals gas, right? We know that there is something wrong happens over here. So we will take this wrong description, we will call it a phase transition, okay? And we'll use this caricature in order to find when exactly the phase transition is going to occur, okay? So the technique of finding the phase transition and correcting the PV curve is called Maxwell construction. Yeah.
אם אנחנו יודעים, לפי זה שאנחנו רואים שה-dp ל-dv הוא גדול מאפס, אנחנו יודעים שהמשוואה של ואן דר ואלס היא לא תמיד נכונה.
Yes.
אז למה אנחנו אומרים שאם, כאילו, איך אנחנו יודעים שרק בתחום הזה בדיוק היא לא נכונה? כאילו, אני שואלת האם המעבר פאזה יכול גם להיות לפני או להיות אחרי?
Great question. So the question is, we know for sure that when dp divided by dv is greater than 0, Maxwell-Boltzmann is not correct. Okay? Right. But, as you say, we can also ask the following question. Who says that if it's not correct over here, maybe there is also additional region over here and over here where it's also not correct? I completely agree with you, and this was what thought by Maxwell, and this is why the technique that we are going to describe over here, it's called Maxwell construction. He's not assuming that only here it's not correct. He's using some general laws about stability, okay, in order to describe the whole region where it's not correct. Okay? So the region where the description of van der Waals is not correct, it's slightly larger than this region over here. Okay? So we need that all of the description of van der Waals will satisfy the different constraints that we have developed so far. How exactly they are going to satisfy that? Well, this is what Maxwell construction does. And Maxwell had in mind this caricature over here. Okay, he says, well, here I don't know what happens. It's a mixture over here. I don't care. It's not a stable situation. I know that the system arrives here and then it jumps over there. So for me, I will describe it by maybe drawing a constant line. But how exactly to find this VA and this VB and this critical P, this is what is done by this Maxwell construction over here. Okay, so this is what we are going to do right now. Yes?
How do you know that you said that in equilibrium, in phase transition, the system is still in equilibrium?
Yes.
So why does when the condition of equilibrium does not?
So I'm assuming that any system, any physical system, no matter what, can be in equilibrium. It's a firm assumption. It holds in 99% of the cases. You're right, it sometimes does not hold, but here I'm assuming that it can be in equilibrium.
Yeah, it's okay, but I'm asking, but why do you assume when the condition לא מתקיים,
is not satisfied?
Yeah, not satisfied, thank you very much. Where there is a phase transition.
Okay, because I know from physical observation that the gas liquefies. Okay? I know it from observations. I know that something abrupt can happen, okay? And voila, it happens somewhere over here. I know it from physics and from experiments. Okay? This is why I assume that this is what is going to happen over here. Okay? So you will see in a minute. You will see in a minute. So what was Maxwell's construction? Maxwell's idea was as follows. Let's look on the Helmholtz free energy. Okay. and dF equals minus S dt, right? Minus P dV, and plus mu dN. Now, if we look on a specific, so we look on a specific isotherm, which means that dt equals to 0. Okay. Now, on this specific isotherm, we plot F when the temperature is not changing. Okay. So we plot F as a function of V. Now remember, what is dF to dV? It equals minus P. Right, so it is smaller than 0. The pressure is positive. dF to dV equals minus P. So we expect something that looks like this. Okay, so this is our expectations. Now, what van der Waals theory or any other theory provides for us? They simply say, well, let's assume that you have something that behaves like this. Okay. Our general constraint said, well, that cannot be because dF to dV has to be negative. In the moment that you have some positive region where when the derivative is positive, it's something non-physical happens over here. So the idea of Maxwell was to say the following thing. Here, a tangent, over here, a tangent, the derivative, or basically the slope of the tangent, right, is dA dF to dV. It equals to minus P. Okay. Now, this is dA. At this point, you can continue this tangent. Okay. And here, the derivative is also dF to dV equals minus P. Okay. This is dV. Now, the pressure is shifting continuously. Okay? What can jump is the extensive parameter, not the intensive parameter. So Maxwell assumed, let's find or define the area, non-physical area, where this description of van der Waals does not hold. Okay? We just neglect everything that happens between this point VB, or basically we cross a tangent, okay, and it crosses at one point, and then it meets the curve at another point, and anything that lies between those 2 points, it's simply neglected, thrown out. Yes?
It's VA and VB from
Yeah, exactly. It's exactly like this. So this whole claim of Maxwell is constructed not on the PV. We will see how it's done in PV, but it's constrained on the F plane. Okay. So Maxwell assumed, well, we somewhere over here have phase A, somewhere over here we have phase B. Okay. And how we obtain those two regions. Okay. Now, so his assumption was, remember, what happens in equilibrium? This is what we have plotted in previous lecture. So we know exactly at the coexistence line. Okay? When the liquid and the gas live together, we have mu A equals to mu B. This is very important. The chemical potentials exactly when we have also liquid and also solid exactly at the phase transition, this has to be satisfied. Okay? So this is one of our general constraints. Okay, so if this is satisfied, why?
Why do we?
Well, because in equilibrium, all the generalized forces has to be exactly the same. Okay? Remember the stability condition.
Where can you see the coexistence line in the graphic?
I cannot see it over here. I can see it on the PT plane. Remember? I plotted not PV, I plotted it on PT plane. So I cannot plot it over here. Okay. This is a point on the coexistent line. Okay, so we look on this guy. We take dt equals to 0, right? This is our only single isotherm. So we have df equals to minus p dv plus mu dn. Now, what do I know that happens exactly on the coexistent line? I know that p equals constant. I know that mu is constant. And T equals specific temperature. Okay? So I'm simply not modifying T. What comes out of this equation if I'm assuming all those constant guys? Simply saying that df equals minus d pv, right? Because p is constant, plus d mu n. Right? Mu is constant, p is constant, so I can take a differential or can take those values inside the differentials. Okay. Let's move it to the left hand side. So we have df plus pv equals to d mu n. This means that f plus pv equals to mu n. Right? Let's divide everything by n. And we have f divided by n plus p v divided by n equals to mu. Okay. Now, what is f divided by n? Let's call it small f, right? It's the free energy per particle or per mole. What is v divided by n? Is a small v, right? It's a specific volume or a volume per molecule. Okay. Now this is mu. So we have, let's for example, we are looking on mu at position A. So mu A equals to Fa plus P VA. Right? From the other point, because mu is constant and mu A equals to mu B, and it equals, according to this equation, to FB plus P VB. Okay. Where's my eraser? Now, then I can compare FA plus PVA equals to FB plus PVB. So what's going on over here? I can extract out of this the P at the phase transition, right? I'm saying at the coexistence line, at the phase transition, the chemical potentials are exactly the same. I found what is the value of chemical potential given that I have the knowledge of the free energy, the knowledge of the pressure, and the knowledge of the volume. Now, the free energy can change from one phase to another. The volume can jump from one phase to another. Exactly at this point, I do not care if I'm in a liquid phase or in a gaseous phase, P stays constant, right? P is constant. And from this equation, I can find this P. So let's solve it, right? So we have P multiplied by VA minus VB equals to FB minus FA. Okay, so P equals to FB minus FA divided by VA minus VB. Or we can say this is simply as minus FA minus FB divided by VA minus VB. This is the critical pressure where the phase transition has to occur. Now, if we plot again our F as a function of V, okay, and we have this behavior, what it basically means, we know that dF to dV equals minus P. Now, we need to find specific point where this derivative exactly equals to another point, which can be somewhere over here. Why? Because we know that at the phase transition, the pressures are exactly the same. So we are going down. The pressure is modified up to a specific point, okay? And we know that after a while, it will return exactly to the same value. So anything that happens in between is not physical, right? Because we know that as we reach the specific or critical point where this is satisfied, right? Where this is satisfied, a phase transition occurs. Okay? So there has to be, let's assume that this is a tangent. So there has to be a tangent to those points. And this tangent, okay, the slope of this tangent is exactly the critical pressure. And we know that it occurs, this is VA, this is VB, okay? This is FA, and this is FB. Okay. So the phase transition, where it occurs exactly at specific points, right? At specific points on this plot, at which I can find that derivatives of those 2 points are exactly the same. Right? So I have to find 2 points on my plot where the derivative is exactly the same, and not that it's simply exactly the same. The derivative is also equals to what? To the differences between those 2 points divided by the differences on the volume. Okay. Yes. So for each, you remember that at the coexistent line, for each temperature, you have to perform this. Okay. So the question is, this is how I find this critical P. But you remember, coexistent line, okay, if I plot P as a function of T, is a line. This is a coexistent line. This is phase A, this is phase B. Whatever I describe to you, what I have to do is I pick a specific temperature, right? I go over here, and by using this Maxwell construction, I can find the critical P. And I'm going to do this for each and every temperature that I have, all right? And I will construct this whole line in this fashion. Sometimes this equality cannot be satisfied. Sometimes this equality cannot be satisfied. Then what do I say? That I don't have a phase transition at the specific T. Think about it. If my phase coexistent line diverges over here, right? For this T, here, there is no phase transition. As simply as that. This is what happens if I will go to larger temperatures, and the line will go like this, right? The F as a function of V. There is no phase transition because this condition cannot be satisfied. P, the derivative, cannot return to its value. Okay, so no phase transitions. Yes?
But if we have a phase transition, like in case of a van der Waals gas,
yes,
from gas to liquid, so the equation isn't true anymore. So why are we still using it?
Because we need some sort of a mathematical model to describe what happens. And it appears that this equation works very well over here, It works very well over there. And it actually provides an extremely good values that when you do this maximum construction, that here the phase transition occurs.
Even if it transforms into liquid, the equation
Yes,
still...
yes, yes. It works extremely well. Okay, so the question is, what exactly do we do and why we do it? We need to find the critical phase transition. Okay. Now, at critical phase transition, we know that there is a specific temperature and a specific pressure where this phase transition occurs due to the coexistent line. Okay, now, how to find this specific pressure? You pick up a temperature, T, you plot this free energy isotherm. So for this specific temperature that you have chosen, you plot this isotherm. Okay, great. Now you need to find a specific pressure when this phase transition occurs, because you do not have the form of this line. You only choose T and you want to find the corresponding P. So what do? You look on this line, you check the derivative, df to dv, okay, and you look for 2 points when this equation is satisfied. Okay? So this is the procedure. You choose T, you plot F, okay, and then you start to explore the derivative of F. Okay? The derivative of F is explored by looking at specific points in one place, looking at another point in another place, okay, and look and seeing if this is satisfied. The moment it is satisfied, you're done. Right? No. This is the construction. Why? Why it is like that and not simply this region to that region? Because we need that at coexistent line, the chemical potential should be exactly the same. Okay? You need to satisfy all the constraints, not simply the constraint that this should have a negative slope. All the constraints has to be satisfied. So this is not enough. You need to take into account the other terms as well. Okay? Yes?
What happens if I can find multiple volumes that can satisfy all of these conditions?
So if you bring me a specific model, I will tell you what happens. Okay? So the Greek answer is you need to take something more complex, and you need to work with molecules that are not single atoms, but more complicated molecules, etc., etc. Okay? Because this equation is satisfied. This is a linear equation because this is what it was obtained mathematically. Well, we have explained it because there are no interactions. Okay? So here, why we obtained this behavior? Because we included interactions. The moment we have no interactions, is simply a line that is decreasing. That's it. Okay, so how to perform this a little bit easier. So this is an explanation, and this is very nice why we are doing this. But how you do it in practice, right? Instead of plotting all those lines and looking on all these derivatives. Okay? And if you do not want to look on the free energy, you want to look on the PV curve. So you have a PV, okay? You have a PV curve, and you have something that looks like this. Okay? This is an isotherm for a specific temperature. T equals T1. Okay? For another temperature, the curve will look somehow different. Okay? So what Maxwell construction, how you do it in practice? Okay? So you need to find a specific VA and specific VB where the phase transition occurs. What we know that at phase transition there is only one single P. Okay? One single P. So how what Maxwell construction it actually does? You need to find this critical pressure, okay? And you simply neglect whatever happens in between. You say it's incorrect. It's absolutely incorrect. The van der Waals description between VA and VB, it's incorrect. Nothing happens. So whatever we do, we find this critical P, and we plot here a straight line. Okay. That's the whole idea. Because phase transition occurs for a specific pressure. This pressure is the same for the liquid and for the gas. So if here are liquid and here are gas, at the critical point they have exactly the same pressures. Okay? So whatever Maxwell is doing is just simply saying this is not correct, and I have a straight line over here, and this region is forbidden. Okay, but how exactly to find PC and how exactly to find this VA and VB? Like, we already have this idea. Well, we can use the free energy, but it's a little bit more complicated. And don't worry, also I do not feel comfortable working with free energies. Pressure and volumes are more intuitive. So how we transform all of this with tangents and etc. to something more simplified, on the PV world. So the idea is actually pretty simple. We use the equation that Maxwell have developed over here. Okay? This equation. So we know that P equals to minus FA minus FB divided by VA minus VB. Okay? So let's multiply everything by VA minus VB. So we have P multiplied by VA minus VB equals to FB minus FA. Okay. What we have on the right hand side? What do we have on the right hand side? So remember, what is F? F is, or what is dF to dV? Minus P. Okay? So dF to dV is minus P. So what stands on the right hand side? This is an integral, right? Because what is FB minus FA? It's an integral minus an integral of dF to dV from VA to VB. Right? This is what we have on the right hand side. So on the right hand side, we have this area. With a minus, with a sign of minus. Right? This is what we have on the right hand side. Questions? Yes?
That means we have the constant and
so exactly. You assume that everything is constant and the only thing that can change is the volume. Right? You remember mu is constant and n is constant and the temperature is constant, and the only thing that is over there that is not constant is dV. Okay? Because if you remember, dF minus S dt gone, minus P dV stayed, plus mu dN, n is not changing. You don't care. Okay? So the only thing that is left is dV. This is why FB minus FA, this is an integral, so this is the area under the curve. Okay? What stands on the left hand side? Questions?
Why is there a minus before the integral?
Why there is a minus before the integral? Because dF to dV is minus P. Okay?
No, but FB minus FA.
Yes.
Is the integral from
Is the integral of this guy. Okay. Fine. But okay, so this is on the right hand side, this guy is over here. But this is minus P. Okay. What we have on the left hand side. What we have on the left, bear with me for a second, bear with me for a second. What we have on the left hand side. Exactly. What is this area is?
For VA to VB and for PC to 0.
So this guy, right?
Yes, and when you take what in the left to the right, you מקבל את ה...
Exactly. Okay. This is good. Very good. So you see, Maxwell said you take the area, the whole area under this black curve. Okay. Under this black curve, you have this area under this black curve, and this is the blue stripes. Great. Afterwards, so what you do, you take the area under the rectangle. So you take the starting point, the end point, and you compute the area under the rectangle over here. Okay, and this is the red area. And what maximal construction means, so this is minus area of VA minus VB. Okay. So the red area and the blue area have to be exactly the same for this forbidden region. Okay. So maximal construction basically tells us you have a curve, find 2 points such that the integral under the curve for these points equals exactly to the approximation, right? What would you do in a class on numerical analysis? Okay, this is the zero approximation for the whole integral. Okay, but when this zero approximation for this integral is exact, this is when you find VA and VB and PC. Okay, where it came from? It came from this maximal construction that P have to be satisfying this equation over here. Yes. Okay. So blue area. Let me write it down. Blue area is integral of VA, VB of AF dV. Okay? This is the blue area. Red area equals to P VB minus VA.
Blue area is not P? It's PDV?
It's not PDV, is PDV, right. It is minus PDV. Minus PDV. The red area is P multiplied by VB minus VA. And then when they're exactly equal, this is how you define your phase transition. Right? So in order to solve, and you will see a solution, clear solution of specific examples with numbers and etc. in the with the TAs. Okay? So I have provided to you an isotherm, and in order to find where the phase transition occurs, you just perform one integral and you compute the zero order approximation of this integral, like you said, you neglect this and you neglect that, okay? And you compare the areas. And when they are equal, this is when phase transition occurs. This is Maxwell construction. Okay? So again, Maxwell simply tells you, you don't care about what's going over here because it's forbidden. Whatever you're trying to describe to me here is not existent. What happens? The only thing that I know that the system can reach over here and then it can jump to this point. That's it. That's the only thing that I know. Here, this is a forbidden region. Forbidden. And van der Waals is wrong over here. And everybody are wrong over here. And I don't really know what happens inside. Now, why do I don't know what happens inside? Because all those theories have some approximations. All those theories assume that the matter that we are looking upon is a continuous matter. But what happens is the molecules, the microstates, are already doing something. Right? So in order to describe what happens exactly at phase transition, we cannot stay with thermodynamics. We have to move on and to describe what happens on the micro world. Up to now, we described only what happens in the macro. In order to dig in and understand what actually happens in the micro, we need to assume something about the micro world, and this is what we'll start to do next week. Thank you.